Okay, so welcome everyone to the second part of the sparse extended information filter. Before we continue with the two remaining steps, I would like to very briefly give you again the big picture. Also, that's kind of a 2 to 3 minute repetition of what happened last week. So the key idea of the sparse extended information filter was to introduce an approximation to the extended information filter, which is the dual representation of the extended Kalman filter, and use it for solving the SLAM problem, but at the same time introduce an approximation that leads to sparse matrices, especially a sparse information matrix. And if we have such a sparse information matrix, we can do most of the operations much more efficiently. And that was kind of the key goal of the sparse extended information filter, to come up with an substantially more efficient, actually a constant time algorithm for addressing the SLAM problem. That in this case means we only need to do a constant number of operations, and this number of operations is independent from the number of features we have in our map. That's kind of the key goal of this algorithm. And it was motivated by the fact that if we look to general Gaussian estimate here of landmark positions, and we look to the covariance matrix, we actually obtain such a dense matrix. That means in this case that the robot pose is correlated with all landmarks, and that the individual x and y positions of the landmarks are correlated with those of the others. However, if we invert this matrix and look into what the information matrix looks like, we actually see this pattern over here. Note that most of those elements which are seen here as white on the slide are actually not zero elements, but they are very small values. And the question is, can we kind of replace this matrix by a very similar matrix? We kind of set those small quantities to 0, and then obtain a matrix which has just a small number of elements, which is sparse, so a small number of non-zero elements, so that we can exploit this fact in all the computations and obtain efficient algorithms. That was kind of the key idea that we want to do. Of course, we don't simply set all those values which are very small to 0. We do it in a different way, but this is kind of the motivation behind that. And the key idea that the sparse extended information filter for SLAM exploits is to separate features into two categories, or actually 3 in the end. We have active features and passive features. So active features are those features where there's a direct link between the robot's pose and those features. So these are features which are typically observed. So if I observe a feature, I obtain additional information, and I add elements to the off-diagonal fields of my information matrix. And there's only a small number of those active features. Typically, it's a constant parameter in the SIFE implementation. And all the other landmarks are so-called passive landmark or passive features. And we don't maintain direct links between the robot's pose and those features. And there's a third category, which are features which have been active before and then become passive, because with those features we have to treat differently, as we will see very soon. Just as a short reminder, what was the effect of a measurement? So in this example, again, this is our information matrix before introducing any observation. So we have some uncertainty about the robot's pose, but no landmark has been observed. We have 3 landmarks, M1, M2, M3 in the environment. And if I measure, for example, the position of the first landmark relative to the robot's pose, I obtain such a link between the robot's pose and the landmark, and this corresponds to this off-diagonal element. If I also measure M2, then I will get those links between the robot's pose and M2. And so whenever I measure something, I add new information in this information matrix between the robot's pose and the corresponding landmark that I measured. So it was a measurement update. So I add additional elements into this matrix. If I looked at what happened during the motion, so this was a step before the robot performed any motion. So what the robot does, it moves, continues traveling through the environment, and is now at the position xt plus 1. And what I do is I want to get rid of xt and only maintain xt plus 1. You can see that as adding xt plus 1 and marginalizing out xt. And if we continue to move forward, that means that those two landmarks become correlated, because I kind of add additional uncertainty into the robot's pose. So the new state of the robot at xt plus 1 obviously depends on xt, but introduces additional noise due to the motion. And this leads to the fact that there's a direct dependency between m1 and m2 given all other parameters. And so some of the probability mass kind of moves down here, and this element was before 0. And so if I look into the motion update, what the motion update does, it weakens the links between the robot's pose and landmarks, because the robot moved, so it gets more uncertain, and knowing the pose of the robot kind of tells me a little bit less where the position of the landmark is located, but it also adds links between landmarks. And these are those landmarks where there were links, direct links to the robot's pose. So those guys become connected. The problem is if I continue this process, I will have connections between all the landmarks and the robot poses. And this is something I would like to avoid, or I want to avoid, because in this case, I wouldn't have a sparse matrix anymore. So, and therefore, the sparse extended information filter introduces an additional step, and this is a sparsification step. And the goal of the sparsification step is to generate and maintain a sparse information matrix. So if we are here in this situation, so this element here corresponds to this link, and what the sparsification algorithm does, it says, okay, I'm going to remove this link over here, and so get rid of this direct link. This is an approximation. And so that there's only a link between M2 and the new pose of the robot. So the effect of this sparsification is that these elements become 0, and those elements here become stronger because an additional link. So if you look to the sparsification, what happens in the sparsification, we go from this kind of matrix to this kind of matrix. But we only do that for active landmarks. So if we have an active landmark, there's a landmark to which we maintain a direct link. Whenever we sparsify our matrix, that means we typically get rid of an active landmark, turn an active landmark into a passive one, because then there's no direct link between the robot's pose and this landmark anymore. And this kind of idea of using active and passive landmarks and doing a sparsification based on those active and passive landmarks is an approximation, because you assume conditional independency between different variables in your state space. And realizing this with this active and passive landmarks was kind of the key idea of the sparse extended information filter for SLAM. And the key idea is, again, the active landmarks are a subset of all landmarks. These are those landmarks to which the robot maintains a direct link. And simply the robot limits itself to the number of landmarks to which it maintains a direct link. And whenever this number exceeds the parameter that the robot set itself, it eliminates one of those direct links, and this is a sparsification step. All other landmarks are passive, which are not active, and the only thing I have to take care of is kind of the landmarks which are active at the moment, but then turn into passive ones, so where these direct links are removed. Because this removal is the sparsification process. So again, if you look to our example here, M1 was a landmark which was active before, now turns into a passive one. M2 is a landmark which is active and stays active, and landmark M3 is was a passive one in this case. Okay, so the key idea to obtain and maintain a sparse information matrix in the sparse extended information filter is to use the sparsification. The sparsification is carried out in every iteration of the algorithm. So after every whatever motion update and measurement update, sparsification step is carried out in order to make sure that my information matrix is sparse. Because all the computations that we did before, which we introduced last week, were essentially relying that the information matrix is sparse in order to be executed efficiently. So, and this step ensures that the information matrix is and stays sparse. Without that step, I could do the operations I did before, or we derived last week. I could perform them in the same way, but they would be computationally costly because the matrices are not sparse anymore. So we come to the 4 steps of the Cyf-SLAM algorithm, and here I have to make a note that we have, there was on the previous slide as well in the book and in all documentations I found an error in this Cyf algorithm. And what was done before that was that the state update was here in the second line. So the second and the third line were swapped, but that was wrong, as also pointed out by Rainer, that this doesn't make sense. Because what happens is we need to, so why do I maintain this mean? Why exists this strange update state estimate step over here? The problem is I need an estimate of the mean for several reasons. The first reason is the propagation of the robot's motion, the nonlinear function g, required the mean as an input. So the first step here, motion update, requires a mean. The second thing is the second step, the measurement update, requires a mean because I need to compute a predicted measurement. In order to compute a predicted measurement, I need to know certain elements of my state vector. In order to compute where is the robot right now, where's the landmark according to my estimate, in order to predict what the robot is going to observe. And also, as we will see, the sparsification step will require a mean estimate. So we need to have the mean maintained, and in the first step, computing the new mean is simple, it's easy, it's exactly the same way as we did it in the EKF. So there's no problem with that. So I actually have the predicted mean for the measurement update. But after performing the measurement update, I don't have the corrected mean anymore. And I need the corrected mean then for the sparsification step. And as a reason for that, there is the update state estimate function over here, which we'll very quickly only look into, which kind of updates the mean, so kind of estimates, approximates the corrected mean given the information vector, information matrix, and the predicted mean. And then we have the sparsification step. So this was swapped in the lecture recordings of last week. This is wrong. This is the correct variant of that. So the corrected mean is written down, is estimated after the measurement update based on the canonical parameters and the previous or the predicted mean estimate. Okay, so as a result of that, now the individual steps are also nicely in line as I designed them before. So we did the first 2 steps last week, which was the motion update and the measurement update. So what we have now is we have, after we executed the second line, we have an information matrix computed, which is potentially not sparse anymore. We have an information vector, and we have the predicted mean, but not the corrected mean. This is what the result of the motion update. And now we have to look what happens, how can we actually recover the mean, the corrected mean estimate based on those quantities. Again, the predicted mean is important for me. It's just what I said before. In the motion model, for the measurement model, and also for the sparsification step. In the motion update, the prediction step, I don't need to do any substantial efforts because I have the old mean, which is a parameter of the Cyf algorithm, and then I just have this delta function. This is kind of the component of this nonlinear motion update function, and I just compute the predicted mean based on that, as I exactly did that in the EKF. So this was the last step of the motion update. We just did it because we needed that, and that's it. So we have the predicted mean directly. The problem now is that we can't easily compute the corrected mean. We can, in theory, compute that, but not efficiently. Because, remember, we have the information matrix, we know the information vector, so in order to compute the mean, we just would need to perform this operation over here. The information matrix here, however, is potentially not sparse anymore, because we haven't sparsified it yet. So this operation is costly. And thus what the sparse extended information filter for SLAM does, it performs an approximation of this operation here. Just to say, how should the correction of the mean actually look like? So Can I correct a few of the dimensions that actually matter to me and get a better estimate so that I can use it in the sparsification step and have a better idea of what the corrected mean looks like. So the key trick in here, in this approximation, why I can do that, is that only a few dimensions are needed of that mean. So what I typically need is the position of the robot and the position of the active landmarks. So it's just a small subset of dimensions which I'm interested in. I'm not interested in all dimensions. That's kind of the first thing that I do. Under this assumption, and given that I have a good estimate of the mean, which was actually my predicted mean, I only missed the last measurement update, I can actually treat that as an optimization problem or as a gradient descent, for example, using gradient descent or any other technique in order to find the minimum or maximum of a function. And in this way, get an estimate for the corrected mean for a few dimensions. And the way this is done is to say, okay, what I'm trying to do is simply try to find the configuration of the mean that maximizes the overall belief. So if I can just expand this, so this is just all the constant factors are not shown in here. So I want to kind of find the best mean estimate. So I already have a starting configuration which is close to what I want to obtain because I already have the predicted mean. I just need to do the last correction step. So I kind of want to you can see there's a local refinement of the mean so that it is better in line with the information matrix and the information vector. Because the information that I'm interested in is encoded in the information vector and the information matrix already. I could simply compute it, but this computation can't be done in constant time. So how do we perform an optimization? What are different ways why I can do that? There are different ways. The first thing is I could set up my objective function. I could compute the first derivative of this objective function. I set the first derivative to 0. Then I obtain a system of linear equations. I solve that and I iterate this process. It's kind of a standard way for doing this. One can apply different techniques, gradient descent techniques, whatever I want. I just do a local refinement of this estimate. And this can only be done efficiently here because I'm interested in a constant number of dimensions. I'm only interested in the current position of the robot and the active landmarks. And all the rest of this of the states I actually ignore here. And again, this is an approximation because in theory this step, if it would execute it, could not be done in constant time because of the number of dimensions that my mean vector has. But as I focus only on a few and I update only a few, I can actually do that. I don't really want to go into the details how this is done because it's kind of a problem which is orthogonal. The important thing to notice here, we do a local refinement of the mean estimate in order to do the last correction step. That would be expensive to compute exactly, and I just kind of do a local search or local optimization with a good initial guess, because I know the predicted mean already, in order to come up with an estimate of what the corrected mean looks like. I will go no further detail because we look into these kind of problems later in the course. So later on in the course, you have pretty good means to understand what's going on and to solve that. But for the material today, it kind of distracts the attention from the main elements of the SIFE algorithm. Therefore, I kind of leave that out. We'll come to this step later during the course when we kind of try to solve a SLAM problem in a similar way. But for now, we kind of say we have a method to locally optimize my parameters with a constant number of dimensions. So this is not a costly operation. Okay, so this step is kind of done, or let's say postponed to a little bit to the future, especially to the time after Christmas where we'll look into these kind of problems. And so the key thing I want to discuss today is how does a sparsification look like? So how can we ensure that the information matrix is sparse, so we only have a constant number of off-diagonal elements, independent of the dimensions of this matrix, and what the sparsification step does, it computes a new information vector and a new information matrix. And the important thing is that this new information matrix is now a sparse matrix. That's our goal. And that is needed, just to repeat that, in order to ensure that all the computations we have done last week can be actually done efficiently, because we always assumed to have a sparse information matrix. Okay, so in order to dive into the sparsification, what means sparsifying an information matrix? Can anyone tell that to me? Told that a few times, just kind of want to...
Ignore unimportant information.
Sorry?
Ignore the unimportant information. Unimportant information has to be gone.
Also, so you want to ignore the unimportant one.
Yes.
Yes. Could you say that a little bit more precise? So kind of, what is the general thing we'd like to do?
Get rid of off-diagonal values.
So exactly. And what does it mean to get rid of some, ignoring some direct links or getting rid of some off-diagonal elements? What does this mean mathematically? So mathematically, it means that we are assuming conditional independence of the variables. So if we have two variables which don't have a direct link, that means their off-diagonal element is 0. That means those variables are independent of each other given all other variables. So if we go from this step to this step, that means the current pose of the robot, x t plus 1, is conditionally independent of the position of the landmark m1, given that I know m2. If I don't know m2, that's a different story. But given that I know all other dimensions, so in this case m2, given I know m2, knowing xt plus 1 doesn't provide me any additional information where m1 is, and the other way around. If I know where m2 is, additionally, knowing where m1 is doesn't help me to estimate the xt plus 1 pose of the robot. So given all other dimensions, the variables are independent of each other if they don't have a direct link. That's kind of the mathematical interpretation of what it means to have a 0 off-diagonal element in this information matrix. And that's exactly the thing we are going to exploit. So if you have a variable, if you have a distribution which contains of 3 random variables, let's call them A, B, C over here. And this approximation, this sparsification, means replacing this P of A, B, C with a different distribution, with an approximation of that distribution, by assuming conditional independence. In this case, that A is independent from B given C. So P of A given B and C is the same as P of A given C. So knowing B doesn't contribute anything to A, given that we know C. And the same down here. P of A given P of B given AC is P of B given C. So this is the approximation that I introduce. So my P tilde, my probability distribution, which is the approximation, should exactly refer to this fact. Okay? So it's just, given that we know everything else, this everything else is C over here, these 2 variables are independent of each other. Okay. So what we do is, we say, okay, P of A, B, and C, we can just factorize this. This is equal to P of A given BC times B of B given C times P of C. The standard definition of the conditional independence. So there's no approximation here. And then I do my approximation. I replace this guy over here with this guy over here. This is the approximation I do in the sparsification. So I say, okay, given that I now see B doesn't contribute any additional knowledge that helps me to estimate A. This is the approximation I do. What I then can do is I can here simply add a term P of C divided by P of C. This is 1. Just added this term over here. And then this simply leads to that P of A given C times P of C is P of A and C. And P of B given C times P of C is P of B given C. And then this one term remains P of C. So the approximation is to go from this belief, saying this belief is equal to this belief down here. This is what we do in the sparsification. This is the approximation that we do. And that is exactly this approximation is something we will now do in the context of the sparse extended information filter, exploiting the individual landmarks, active landmarks, passive landmarks, and active landmarks that turn into passive ones. Is there any question at the moment? Yes, please.
In the first line, you said P of B given C. This we know, but we have to approximate P of A given C.
So the first line is, this is just an exact transformation from here to here.
Okay.
So this is just the definition of the conditional probability. So it's kind of, if I have P of A and B is equal to P of A given B times P of B. And this is exactly applied there. Okay. The only difference is that we additionally have a variable C involved. Yep. And this is kind of done twice, so 2 steps. Yep. There's 3 variables, the first 2 and the other 2. So the first line is exact. There's no approximation in here. Yeah. And then the approximation is transforming this term into this term. And this is, I assume that A and B are independent of each other given C. And this exactly corresponds to kind of getting rid of those, or having 0 off-diagonal elements between A and B here. So A could be the robot's pose at time t+1 in the previous example. B would be the landmark M1, and C would be all the other dimensions, in this case landmark M2. Okay, any further questions? Yes, please.
In the second line, why can't I use it already there? Why do I have to divide by P of C? Why can't
I can leave it like this and be happy with this one. These are all just exact transformations.
But you said in the third line you can use P of B given C times P of C is the same as P of B given C. So we can
Okay, I could leave here actually P of B and C. So I could have saved those steps over here. Yeah, so this here is exactly P of B and C. Is this your question? Yeah. So it's exactly the same, but you're right. I could have only expanded this term and then leave here P of B and C. Yeah, I would have less terms in this equation. Absolutely right. This is possible. It means it's equivalent, but you're right. It would become more compact to write.
That's easier to understand this way.
Okay, any further question? Okay, so we kind of, now we understood what this sparsification does. It assumes conditional independence between subset of, or between 2 variables given the rest. And this is now something we want to exploit in CipSlam in order to obtain an information matrix which is sparse. So our goal is to approximate our information matrix so that it becomes and stays sparse. And the way this is done is by only taking into account the direct links between a small subset of the landmarks. And these are exactly my active landmarks. And this also has an effect that the number of links between individual landmarks also is limited, because the additional links between those landmarks are created for landmarks which have been active at the same time. And not all landmarks are active at the same time. As you can see, there's a small sliding window which goes with the robot and is in the surrounding of the robot. So you will have landmarks that are all locally connected with their neighbors, but it is a small number of connections that these landmarks will have. It's kind of independent of the size of the overall environment. So if I just have a local scene where, let's say, every landmark has whatever, 10 neighbors, if I expand the size of the environment by whatever, replicating this room 1 million times, it doesn't change the local structure. And so every landmark has only, on average at least, a constant number of different of direct links to other landmarks, and it's independent of the overall size of the environment or the space that I'm going to map. And links are created between landmarks which have been active at the same point in time. Okay? Okay, so again, so the key trick is only considering those active landmarks during our update steps. So in the update steps, like the motion update, I'm only, or no, that's not true. So the key trick is to have only direct links from the robot to the active landmarks. And if I only have direct links between them, then the motion update automatically enforces that only those active landmarks get connected with each other through direct links and not the other landmarks. Okay, so this slide we already had. Just to remind you, active landmarks are just a subset of all landmarks, and all the others are passive landmarks. And we actually go right now a step further. We have landmarks M+, which are the active landmarks. We have M0, which are the active ones which now become passive ones. And then we have a minus, which are those which are passive. Okay? So these are kind of the three quantities which are important now for our sparsification. Okay. So we said we want to remove the direct links between the robot's pose and the active landmarks which become passive. So all landmarks which are active and stay active, don't have to do anything. All landmarks which are passive before and stay passive, we don't have to do anything. And we only have to, in the sparsification step, remove the direct links of those landmarks which are active but now turn into passive ones. Why do they turn into passive ones? Because the robot, for example, observed a new landmark which was passive before, then this becomes active, and as I only am allowed to have a constant number of active landmarks, I have to throw away one. Probably the one which I haven't observed for the longest period of time. It's kind of like I have just a buffer which is sorted according to the time step when I have seen those landmarks, and when I ever add a new one, I have to throw out the oldest one. It's kind of one way for maintaining your set of active landmarks. So whenever one is kind of thrown out of my list, I need to make sure that there are no direct links anymore to the robot's pose, otherwise I would get my dense matrix. And again, this is equal to assuming a conditional independence given all other landmarks between the robot's pose and this landmark which becomes passive. And this operation, is important to note that this does not change the links of the passive landmarks. So all landmarks which are passive, they stay passive. So I don't add any new links to whatever passive landmarks. Otherwise, my matrix would become dense again, but that's nothing which happens. So I rewrite now my posterior P of xt and m, given all my data, into 4 variables: the current pose and my 3 different categories of landmarks: active ones which become passive, and passive ones. And now I kind of continue the next slide with getting rid of, or with performing this sparsification that we have seen with our variables a, b, and c before. Okay, so what I do, so I just dropped all the dependencies on the observations and controls here. So think as if they would be there, just have not written them down. Otherwise, it gets a little bit too, the slides get a little bit too crowded with variables. Okay, so this was the step we have seen in the previous slide. So we just expanded kind of m by saying it's m plus, m0, and m minus. Then the next thing is definition of conditional independence, exactly what's written here still on the blackboard. In this case, a corresponds to xt, and b corresponds to the 3 variables over here. So we turn the joint belief, p of a and b, into p of a given b times p of b. Well, that's nothing bad has happened over here. Okay, now let's look to the to this estimate over here. What does this strange equals 0 means? The thing is, there are only direct links between the robot's pose and the active landmarks. And those, the active ones which become passive, which I want to get rid of. So there are only direct links between xt, m plus, and currently m0. There are no direct links between xt and m minus, right? So whatever value those take, I don't care, because it doesn't impact my current estimate. So I can do that. I can assume I set them all to 0. Just at least in this expression over here, say, okay, they are all 0. They're all 0, 0, 0. That's what I assume for the moment for doing these operations. Because I don't need them. Whatever value they are, I just kind of, I condition on them, and I just can set them to 0 because I know that they won't impact the other pose. Okay? Okay. And then now, okay, so exactly that's what I just said. Given the active landmarks and the passive landmarks do not matter for computing the robot's pose, so I can set them to 0. Then the next thing is, this is now the sparsification that I do, is I assume a conditional independence between the robot's pose and those landmarks which have been active before and now become passive. This is now the sparsification that I do. I assume, given all other landmarks, so given the active ones and given the passive ones, which are all other elements of my state space, the robot pose and the guys which become passive or independent of each other. This is my assumption. This is my sparsification assumption. Given everything else, xt and m0 should have no direct links. Right? This is the assumption I do. So now I make the mistake here, or it's an approximation. So it's not exact. So I introduce an approximation error here. And this is what the sparsification does, because I ignore conditional independence. Therefore, m0 simply disappears here. I don't need it anymore because I know, well, this is my assumption that, this is my assumption that the robot pose is independent from m0 given all other landmarks, the active ones and the passive ones. Is that clear? This is kind of the key step in here. Okay. And what I then can do is I can just rewrite that in a similar way that we have done that before. I can say, okay, this now, I can rewrite, this term stays exactly the same, and this term over here can be rewritten in the joint belief of xt and m plus given m minus divided by m plus given m minus equals 0. This is something like exactly the same thing we had with this c before. P of c divided by p of c. This exactly leads to this expression over here. And this is now my sparsified belief. This is p tilde of xt and my belief. So the question is, how do I compute this term over here? Well, this is now the expression that I need to compute. Right? So I need to replace my current information matrix by the information matrix which corresponds to this expression over here. Okay, so let's have a look how we can actually do that. So this is just a summary that we see what happens, just a summary of what was written on the previous slide, except that I just added these, the observation and the controls, just to have it kind of formally correct written on the slides. And so the key trick is to replace the information matrix, there's still now this Gaussian distribution, this information matrix here, which is this tilde, so this is the approximated information matrix, by a sum of 3 information matrices, omega 1, 2, and 3. And they correspond to these individual elements in here. So they correspond to these individual beliefs. And now I just have to compute what are the information matrices of these individual terms, and then I can actually then set them up. And this can actually be done, it's not too difficult. So the first thing I do, I take my original information matrix, the one I had before, and I condition it on m minus equals 0. So this gives me a new information matrix, which is the belief P of xt m plus m0 given m minus equals 0. This is what happens over here. Right? Changed it into the belief. So the first step is this sigma 0t corresponds to P of xt m plus m minus 0, sorry, given m minus equals 0. Just compute the conditional, and then I get this information matrix which corresponds to this belief. Okay? Okay, what I then do is I marginalize out m0. So this gives me an information matrix omega 1, which is just the integral over my m0. So this is P of xt m plus, okay, or just marginalize it out, so it's simply not there anymore. m0 m plus given m minus equals 0 d m0. So this is the information matrix which corresponds to this belief. And then I do exactly the same. I marginalize out x0 and m0 from this belief, which gives me my information matrix 2. So that means I take the information matrix I have here, which was this guy over here. Right? From this guy, I get rid of x and m0. So I get rid of x and m0, so only m plus remains. Which then leads me to exactly this term down here. And then I take again this belief and get rid of, marginalize out xt. So this gives me to this belief, which is this term marginalizing out, oh no, this I do from the original information matrix. Sorry, not from this term. I just marginalize out x, so marginalize out x, so the rest remains. And I just can apply the marginalization rules and conditioning rules for information matrices for the Gaussian that we had discussed in the beginning. So one is easy in information form, the other one is more expensive in information form. This exactly just performs these individual operations over here. And then I can generate my final information matrix. So I already have the information matrix, a sparse information matrix for my belief. And if I have that, then I can say, okay, now I can compute my sparsified information vector by using my, so the information vector which corresponds to the sparsified information matrix. By taking this sparsified information matrix, multiplying it by the mean, that's what I would need to do. So I can expand this, this term over here into this equation over here, which just take the original information matrix, subtract it, so this is 0, plus the term I have here times the mean. So it's just adding, it means just adding a 0. So I can expand that, say, okay, this is the old information matrix times the mean. This is the, and this is the difference between the sparsified information matrix and my the original information matrix times the mean. So this again gives me the old information vector, and this is the difference in the information matrices. If I write it in this way, this can be very efficiently implemented, because what I do here is say the C tilde, which is what I want to compute, is just my old information vector that I had, plus just those elements where the information matrices differ, times some vector. So this guy here will be basically 0 everywhere, except of the few landmarks which changed. do the sparsification. So where the sparsification lead to a change in the values of the information matrix. So there are just a small number of elements which are non-zero. And so I can just update my information vector very efficiently without having to compute here these matrix operations in reality. That's kind of the key trick again. So just a small number of elements here, the difference are non-zero, because just the difference between the sparsified and the non-sparsified matrix. We're just getting rid of maybe one or two active landmarks, which became passive. So just a few elements are set to 0, and a few elements have changed their value of the active landmarks, but the rest stays the same. So it's just a very small and local change. Okay. So this is then what the sparsification algorithm looks like. This guy here, this ugly block, is just the individual conditioning. And so this was the conditioning, and the rest were just the marginalization steps of the information matrix, marginalizing out the individual values. And these matrices F here are just these projection matrices that we used already. So far, we only used it for the state, so we used Fx. But now we can, okay, Fm0 is just everything 0 except those elements which correspond to the landmarks, which are the active ones which become passive, just M0, and the same thing for different subsets. So it's just kind of these projection matrices which are 0 everywhere, just have the ones in a small area. So these two steps here correspond exactly to this operation that we had before. Just haven't expanded that, but it's just, I don't want to say straightforward, but just applying the marginalization and conditioning rule. So it takes you a page to derive that, but the individual step, there's no black magic in there in obtaining with these maybe a bit scary formulas. It's really just marginalizing out variables and conditioning on a subset of the variables. That's pretty good. We're done. All the important steps of the sparse extended information filter have been done. So what we have now is we have an algorithm which performs all this operation in information space and additionally maintains the mean, which I need for basically all operations. It does the motion update in constant time, assuming that the information matrix is sparse. It does the measurement update in constant time, assuming that the information matrix is sparse. It performs the state update, nearly constant time, because it just involves a constant number of dimensions, but it's an iterative process, so there's a certain number of iterations I need to carry out, or search steps in my gradient descent. And of course, you can limit that, but you don't know if this guy has converged or not in the process. So take it a little bit with care, but if you generate an implementation which just says, okay, just execute a certain number of iterations in my process, and then I simply stop, then I'm close enough to the estimate I want to have. I anyway do approximations. This really doesn't affect the estimate as much, and this is actually the case. So just a few iterations are typically sufficient to come up with a good estimate, and the approximation error that you introduce, which comes from this step, is neglectable compared to the sparsification that you do. Okay, so just an effect on what's the effect of this sparsification. What you see here on top is the standard result what an EKF would generate, or in general extended information filter. So you see this. What you see here is a graph with these are landmark poses, and this is the robot pose, and you see the connections. And the black ones here are the active landmarks. So in the trivial case, every landmark is active. There are no passive landmarks, no M minus, no M zeros. So it's just nothing is sparse anymore. So it's exactly the result that the extended information filter or the extended Kalman filter would produce. And this is the result of the sci-slam algorithm just fixing, I think, to 6 active landmarks. Although you cannot see that this is a constant number, but you can see it's much smaller, the number of edges you have in here, to this guy. And so this is the corresponding information matrices. It's hard, actually visually we don't see a difference, but the real difference is here now are a lot of values which are exactly 0, and here are values which are small but not exactly 0. It's kind of the main difference between them. And also if you look to the covariance matrix, you can see this one is a little bit lighter or brighter. I'm not sure if you can see that, but that's kind of the difference. So you may expect that the difference is not too small, but there is definitely a difference in between both estimates, because we have done this approximation of sparsifying our information matrix. So we ignore correlations, not correlations, we ignore, we assume conditional independence between variables given all the rest. That's the approximation that we have done. Okay, if you now compare SIFE-SLAM to EKF-SLAM, we have a roughly constant time algorithm. I use this roughly because it's not exactly constant time due to the recovery of the mean, with the quadratic complexity for the EKF. So this is a great improvement in terms of computational resources that I need to spend for every update step. So it's not quadratic in the number of landmarks anymore, it's constant. So it's a really, really major win. Because no matter how big the environment is, it works at roughly the same speed. And with the other one, the computational resources that you need to spend grows quadratically, which quite quickly, which can become intractable quite quickly. However, we have a less accurate estimation system. So we made approximations in there compared to the EKF. So the performance in terms of the accuracy of our results decreases. It's just a result of the approximation. And we just have a linear memory complexity, so we still need to store all landmarks. And we have a sparse information matrix. There's a linear number of elements in there. So the memory storage that I need is linear, but I only need to update a constant number of those of these vectors and sparse matrices. So therefore, it's constant in every step, but I have a linear memory complexity that I need. But still better than the quadratic memory complexity that the EKF requires, because it needs to store the full dense covariance matrix. Since I only need to store a sparse matrix, I can do the linear memory complexity compared to quadratic complexity of the EKF. Okay, let's see how this changes the computational resources that I need. So what you see here, so these are the computational resources that need to be spent on the EKF. There's a number of landmarks. So for, in this case, 400 landmarks. An update step takes around 1 second for the EKF, whereas the SIFE stays much smaller and stays, so if some overhead in the beginning, but then it stays roughly constant and will continue like this. So, of course, and this grows through the sky quite quickly, where this guy stays roughly constant. So this is a big win. Next thing we can look to the memory usage. And again, we can at least roughly see the quadratic pattern we can see here versus the linear pattern which we see here. Because we really just have to store, for every new landmark that we add, a constant number of dimensions in our information vector mean, just let's say 1 landmark, 2 new dimensions. And we have a constant number of elements in my information matrix. So there's really a linear growth over here. So this were two cases where we have the clear win for the SIFE-SLAM compared to the EKF-SLAM. But if we look to the approximation error that we do, we can actually see, so this is the EKF. If we compare to ground truth, this is a SIFE. We can actually see that the SIFE makes an error. But this error obviously depends on the number of active features. If I set the number of active features towards infinity, or the number of landmarks I have in the scene doesn't need to be infinity, then these curves should be on top of each other. And you can actually plot the accuracy of the this is the computation time it requires for the which grows with the number of of active features. So this is in this case whatever EKF. I think the example had 60 features, which was shown before. So this is the update time for the EKF. No, it must be more. I'm not sure to which data set this corresponded to. Maybe it was this Victoria Park data set. I'm currently not aware of that. But if we look to the number of active features, we can see that up to 10 active features are still substantially substantially faster than the EKF. So if we, of course, this simply means all. So this curve would grow something like this. And if I look to the approximation error that I have in my estimate versus the active features, you can see if I have a small number of active features, like 4 or 5, I make really big errors with the SIFE. But as soon as I increase that, so kind of whatever from 7 to 10, the error is really small and it's hard to identify the difference between both. So whatever, this area seems to be kind of a reasonable compromise between small approximation error and efficient runtime. So somewhere along these lines. So to sum that up, what I presented this week and last week was the sparse extended information filter for SLAM. And this is a variant of the extended information filter which allows us to maintain sparse information matrices. And due to the sparsity, we perform much more efficiently. The sparsification means that we neglect or ignore direct links in the information matrix. So assuming a conditional independence given all the other variables, this is definitely an approximation. So we lose, the quality of our solution decreases, but we are much faster in actually computing it. And this is a constant time algorithm, which is quite remarkable in the context of SLAM, assuming that we have known correspondences. If I need to search for correspondences, this may change the game a little bit because I may need to look into a larger number of landmarks to identify what is the landmark that I currently observe, to which landmark does this correspond in my map. This can be more costly. This depends on the setup that we have. So that you, whatever, may need to maintain efficient lookup structures like KD trees or something like this that introduce additional complexity, but we still can do that actually fast. But again, the quality is smaller compared to the extended Kalman filter SLAM because of the approximation that I do. The Psi framework itself is not always directly applicable to other problems. I mean, if you have another problem which has a very similar structure than the SLAM problem, that means you have only a small number of dimensions which are updated in the prediction step, and you only have a small number of variables that are observed by a measurement update because you have, let's say, a sensor with limited range. Then you can actually apply that. But it's not kind of an as general estimation technique as whatever the EKF. Or you can do it, but then it kind of loses the great performance that it has. So it's something to keep in mind. It explicitly exploited some of the properties of the SLAM problem. And therefore, it was successfully used in SLAM, but at least I'm personally not aware of a lot of other applications of this framework. Because we have this special pattern that we say, we have only a small number of dimensions which are changed according to the update step, which is just the position of the robot. And I, in every point in time, observe only a constant or limited number of features or of other variables, whatever I'm going to observe or estimate. In this situation, this technique can be used in an effective way. Any questions about that? Yes, please.
We said when the landmarks turn passive, when they were active, we delete the links between the robot's pose and the landmark. And we make the link stronger between the landmarks. Do we do that automatically in the
Yes, so the deletion was just, when I said deleted, it was something like which I used in my words to make it easier to grasp for you. Okay. Where this goes away is exactly in this marginalization and sparsification steps. Okay. And so because I really marginalize it out, and then if you marginalize out a variable, what happens is all the neighbors of this variable which had direct links become densely connected with each other. It's like in a marginalization, if you look to a Gaussian Markov random field, when you marginalize out a variable, you get this elimination cliques of where all neighbors are connected. This is exactly the same what happens here. This is just kind of hidden in this marginalization and conditioning rules here, what I said in terms of we are deleting those links. This was kind of an informal way of saying what happens here. Therefore, in the beginning, we also had kind of these errors where kind of information goes from one element to the other element, if you remember that. Yeah. This is something which results from these steps. So it's not kind of a dirty hack which does it. This results automatically from the conditioning and marginalization rules of the Gaussian distribution in information form or in the canonical form, in the standard moment form. Okay. Yes, please.
Does it help if we have non-constant active landmark? I mean,
what do you mean what is non-constant active?
When we observe more landmarks, then our active landmarks number increases to the number of observation. And when we see less landmark, the active landmarks
So you mean if you automatically adapt the size of your active landmarks? So of course, the thing is, the bigger that set is, the better you are in performance. So if you shrink it, you get worse. You may be a little bit faster, but anyway, every step is a constant time step. So at least from the computationally complexity point of view, you don't win anything, but your solution gets worse. But of course, if you just count the number of instructions that your processor needs to do, that will be less if you reduce your set. So I would say it's not worth doing it, but your quality will be worse, but you will spend you will do a few less operations. So I mean, the question is, do you need that? If your processor is exactly at the limit, you can do that. But
in the case that, for example, one special case, we observe more landmark bigger than the constant number of active.
Okay. So then I misinterpreted your solution. Then you want to kind of increase the set of active landmarks temporarily. You could do that. Yes. I cannot tell you how big the impact is on the result because I haven't tried it, but. Yeah, it's simply hard to estimate how big the effect is, and probably depends very much on the exact sensor setup. How much information does the measurement provide you compared to other information that you have? So I guess it's very, very problem and instance specific. So it's hard to comment on this in general, and I haven't tried it, so it can just give an educated guess to you and not tell you exactly what it would be. Okay, so if you want to look in more detail in what happened here, the best resource is actually Probabilistic Robotics book on the sparse extended information filter. But be aware there are quite a couple of inaccuracies in the book. So if you read the book, open your browser, look up the errata page, and skim through the errors which are in your printing, because there have been quite some updates on that. So that if you read through it, you say, oh, it's completely different to what's written on the slides. I would trust, in the current state, given the last printing of the current printing of the book, I would trust the slides much more because some of the errors are fixed. If you find any other errors, let me know or let the authors know, and they will end up at the errata page. But yeah, just if you see a discrepancy, check the errata page before you complain. That's kind of my advice to you. Okay, anything else at the moment here? Okay, then I'll just